All right, hello everyone. Just wanted to have a follow-up to my last video about confidence intervals for proportions. And this one is about confidence intervals for means. So if you watched my last video, you would have seen what a confidence interval is and why we talk about them. And so the short answer to that is that a confidence interval tells you where the true parameter is likely to be. It essentially means, so if we want to find a 90% confidence interval, we have a procedure for collecting data and making an estimate that will 90% of the time contain the true mean value. So this does not mean, for instance, that 90% of trees would have a height in that interval. We don't know that. It could be many more or many less. It'll usually be much less than that, as you could see if we had sort of ordinary data. And we also want to say, well, how can we do this estimation now for a mean? And so let's actually put in what we had already. So I realized that the typing sound was kind of obnoxious in the last video. And so I've now set up all the stuff that we need to have. And so there's three main inputs that we need, actually four. One is whatever our sample mean is. So in this case, we have a sample of 55 trees. The mean height is 10.6. And then we have a standard deviation of 3.2 and a sample size of 55. And we want to find a 90% confidence level, or whoopsie, 0.9. So last time when we looked at proportions, we looked at, well, what's the standard error of a proportion? And we had a formula for it. We want to say, well, what's the standard error for a mean? You say, okay, well, if you remember the central limit theorem, we know that the mean of sample means is the overall mean, which is really nice. So our confidence interval will again be centered at the true value of the mean, which is great. And the standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of n. Now, in this case, we don't know what the true population standard deviation is. Now, there is actually a technique that if you did know the true standard deviation, you could just use a normal distribution using this as your standard error. But if you don't have it, then the best you can do is estimate it using your sample standard deviation. And so we're just going to estimate it by taking the sample standard deviation divided by the square root of the sample size. And now there is one adjustment, though, that we will make. We're not actually going to use a normal distribution this time. And the reason why is because when we found this standard error, we didn't do sigma over the square root of n. We did s over the square root of n. And that's the formula that you see in your textbook is s over the square root of n. It's our sample standard deviation, not the true population one. And it's possible, especially in a small sample size, that our sample standard deviation is not the same as our true standard deviation. It might be quite a bit smaller, in fact. And there is, in fact, a little bit of bias there. And so instead of using a normal distribution, we're going to use something similar known as a t-distribution. And with a t-distribution, you need to get a number of degrees of freedom. And so the degrees of freedom for a t, though, is actually quite straightforward. You just take the sample size and you subtract 1 from it. You might say, well, what is degrees of freedom? Well, the degrees of freedom is effectively sort of the number of values that you can change while still keeping the parameter the same or your statistic the same. So if we were talking about the mean, you could change 54 of your values or set them to whatever you want, and then you could always set the 55th value to a specific value that makes the mean whatever you want the mean to be. And so that's why you have 54 degrees of freedom. And so the critical value, remember on the previous one, we took alpha over 2 and said, well, what's the probability, or not the probability is alpha over 2, but what is the test statistic associated with that alpha over 2? How many standard deviations do you need to go from the middle to get alpha over 2 as your tail, where alpha, again, is 1 minus the confidence level. Because the confidence level is how often you capture the true mean, so alpha is the probability that you don't. And so we can just use the complement rule and subtract that from 1. And so similar to the one with proportions, we're going to use the inverse. So, but instead of using the normal inverse, we're going to use the t inverse. All right, and so we can say that the critical value is the t inverse of the alpha over 2. And alpha is 1 minus the confidence level over 2. All right, so we can just say equals t dot inv. All right, and then the probability is 1 minus the confidence level divided by 2, because remember it's alpha over 2. And then we have our degrees of freedom. And I knew that was going to happen. Remember, that's the same thing that happened last time. We said, oh yeah, we just calculated the value that's over here, the one to the left. And so we actually want the positive critical value. So we'll just multiply by -1, and that would be the area on the right now. And then, well, that's the number of standard deviations from the mean that you need to go. And that's the size of 1 standard deviation of your sampling error. Remember, the sampling error is the standard deviation of your sample means, and thus is the sort of average amount of error between your sample mean and the true mean. And so the margin of error is the 1 standard deviation of error times the number of standard deviations you need to go to capture, in this case, 90%. And then, just like before, the confidence interval is always centered at whatever your sample statistic is. And then you do minus the margin of error and plus the margin of error. And we can hit enter. All right. So this tells us that we are 90% confident that the true mean height of this tree species is between 9.88 feet and 11.32 feet. All right, so note this does not mean that 90% of trees have a height in the interval. But what it does mean is that we're 90% confident that the true mean height, all right? So 90% of the time that we create such a confidence interval, the true mean will be within that interval. Also note, the sample mean is contained in the interval 100% of the time. So that's another sort of misunderstanding that I sometimes see, is students will interpret the confidence interval to say 90% of the time that we make this confidence interval, we'll contain the sample mean. No, 100% of the time you do, because the sample mean is the dead center of the interval. What we're actually looking for is how often we capture the true mean. And that's all that a confidence interval tells us, is how often we capture the true mean, or that we're likely to have the true mean somewhere within this interval. It does not tell us anything about the individual trees, where they are, or anything like that. All right. And so, again, we can sort of play around with it. And one of the great things about these templates is that you can sort of just copy and paste these formulas down and sort of play around with these numbers and see what changes. So like if I change the standard deviation, notice a larger standard deviation will give us a larger standard error. A larger confidence level will also, well, it won't change the standard error, because the confidence level doesn't change the standard error, but it does affect the critical value, because you want to contain more of the region inside. And therefore, we still get a larger margin of error because we've increased the critical value. If we were to change the sample size, notice we increase the sample size, we decrease the standard error, and thus decrease the margin of error. Because the larger your sample size is, the more likely it is that your sample mean is close to the true mean. And similarly, if we decrease the sample size, then we have a much larger standard error, and a therefore much larger margin of error. I should also note as a caveat that if you have a small sample size, then you want the underlying population to be normally distributed. And so that's another little note. If the sample size is small, this is only valid if the underlying population is normally distributed. But for large sample sizes, that doesn't matter. And this also comes from the central limit theorem, which, if you remember what the central limit theorem told us, it didn't just tell us these two facts, which were very important, but it also told us that if the sample size is large, above 30 was our rule